Okay, welcome to question 10. Okay, this question is about stress-strain graph. Stress-strain graph. Okay, a metal wire of 1.2 millimeter diameter. Okay, this is millimeter. You need to change to meter later on. And 3-meter length. Give you the original length. Is stretched by forces of various magnitude. The stress versus strain graph of the wire is as shown in this figure. Find the Young modulus for the metal of the wire. Okay, I want to find the Young modulus of the wire. Okay, first of all, what information we have? We have the diameter, but in millimeter, you need to change to meter. We have the original length, L0. And this is a stress-strain graph we have. But be careful with all the exponent. Some students are so careless and they just don't see the exponent here. I don't know, they should maybe they should check their eyes whether they are blind or they have, so you should make sure you check this exponent. And don't get it wrong during your exam. So now I want to find the Young modulus for the metal. So I have a stress-strain graph. So, the Young modulus is actually the gradient of the graph. The gradient of stress-strain graph is the Young modulus. Okay? So, Young modulus is actually stress over strain, which is the gradient of the stress-strain graph. So, just find the gradient and you get the Young modulus. Okay, so the stress, I take 10.5 exponent 7. Okay, so 10.5 exponent 7 Pascal. Don't forget the exponent. And 1.5 is not just 1.5, but it's 1.5 exponent negative 3. 1.5 exponent negative 3. That's a strain. Do we have any unit? No, you see, no unit. Strain has no unit. No unit. So what do I get? What's the answer for Young modulus? Yes, the answer is 7 exponent 10. Pascal also. Or also can write as Newton per meter square. Okay, it has 2 units. Either Pascal or Newton per meter square. So 7 exponent 10. Okay, now there's a Young modulus. So now I want to find what is the applied force if the stress of the wire is 10.5 exponent 7 Pascal. Okay, what is the applied force? What is the applied force if given stress? This is the stress, given stress. So given stress, so stress is force over area. So I can find the force. Required. So I want the force over area. Is there any area? No, give us diameter. Give us diameter, expect us to find the area. From diameter, you get area. So if something have diameter, of course it's a circle, isn't it? If it has diameter, of course it's a circle with a diameter. So I want to find the cross-section area. Okay? So we have diameter, want to find the area. So its area is pi d squared over 4 for a circle. Okay? For a circle. Where diameter means it's a circle. So pi d squared over 4. So remember, your diameter given is millimeter. So the milli, you need to change to exponent negative 3. Milli change to exponent negative 3. So, and then you just substitute the diameter 1.2 exponent negative 3 into this formula pi d squared over 4. Then you can find the area. So let us straight away get the area after you substitute 1.2 exponent negative 3 into the diameter. So you calculate pi d squared over 4. the area you will get 1.131 exponent negative 6. That's the area, cross-sectional area for the circle, pi d squared over 4. Okay, so I got the area. And the stress applied is 10.5 exponent 7. 10.5 exponent 7. So just substitute inside. 10.5 exponent 7 Pascal. Force over area. Area is 1.131 exponents negative 6. Okay, substitute this one inside. Then I can get my applied force. My force applied, which is 118.755 Newton. That's my applied force for distress. Okay, for distress. So I can say this 10.5, this 10.5 stress is equivalent to force 118.755 Newton. Yeah, the force Newton. Now, what is the extension of the wire if the strain of the wire is 1.5 exponent negative 3? That means this one, this strain. At this strain, I just now asked to find force. Now he asked to find extension. You know, extension actually is equivalent to the strain. So under this strain, 1.5 exponent negative 3. Okay, excuse me. Under this strain, 1.5 exponent negative 3. What is the extension of the wire? So you just use the formula strain equal to elongation over original length. This is the original length. So I have the strain 1.5 exponent negative 3. So just substitute inside. Okay. 1.5 exponent negative 3 equal to elongation over original length. Original length is original length is 3 meter. Okay, original length 3 meter. This is the original length. Yeah, 3 meter. So 3 meter. Okay. So what's my elongation? My elongation I get 4.5 exponent negative 3 meter. So my elongation is this. For this strain, so what I can say is for this strain is equivalent to my elongation 4.5. 4.5 exponent negative 3 meter. Okay, for this strain. So now sketch a graph of force versus extension graph for the wire. So now I want the FE graph or FX graph. So my graph is FE. You can label as E or label as X. No problem. Both has the same meaning. Elongation is the same as extension. E or X is the same. Actually, it's a Hooke's law. F versus X graph. But since he's mentioned versus extension X, since he used X as symbol, then this time we also use X lah. So this time we also use X meter. Okay, because he mentioned X, we just use X lah. It's the same meaning as E. Same meaning as our E. So just now my force is equivalent 118. Just now I got 118, isn't it? Force 118 is equivalent to the stress 10.5. So so this just put 118. And this is 118.755. 755 Newton. This is the force for this stress equivalent to 118. So it's 118 lah. Okay. Now how about the strain? For this stress, it has this strain. This strain is 4.5 exponent negative 3 elongation. So this part is 4.5 exponent negative 3, 4.5 exponent negative 3 meter. Okay, so for this stress, it has this strain. So for this force, it has this elongation. 118 correspond to 4.5. 118 correspond to 4.5. Okay, yeah, they are proportional. Okay, that's it. That's the if you want to make it simpler, also this exponent negative 3, you can make it millimeter. We just put 4.5 here, and then here you put millimeter. Also can. Okay? This is the answer. Now, E. Determine the strain energy stored in the wire if the strain is 1.5 exponent negative 3. That means if the strain is this value, 1.5, if the strain is this value, 1.5 exponent negative 3, means this value, 1.5 exponent negative 3. So what is the strain energy stored in the wire? 1.5 is correspond to 4.5. So that means also under this elongation lah. Also under this elongation, because 4.5 is correspond to 1.5. If given this strain 1.5, what is the strain energy stored? So I want to find U. I want to find U for this strain, this given strain. This strain is correspond to 4.5. So which is this one also, this elongation. So that means I need to find area under the FE graph from 0 up to 4.5. That means I need to find this area. I need to find this area here, the area, this area. Area under this graph, under the FE graph. That's the strain energy. Okay? Under this strain 1.5, which is also 4.5 elongation. So the strain energy is the area under FE graph. Under the FE graph, which we have just built just now. Yeah, which we have just built just now. The area under FE graph. Area under FE graph is half FE. Half times force times elongation. So just take this value, this force and this elongation, multiply half, you get the answer. Okay, so half times this force 118.755 times the elongation 4.5 exponent negative 3. So what's my strain energy got? What is the strain energy I get? 0.267 joule. That's the strain energy stored. Yeah. So under the FE graph, you can get the strain energy, which is 0.267 joule. Okay. Now, question F. Question F, determine the strain energy per unit volume. Oh, now I want the strain energy per unit volume. If the strain is, again, the same strain 1.5 exponent negative 3, again the same strain. That means again the same strain 1.5 exponent negative 3. What is the strain energy per unit volume stored in the wire? So for this one, strain energy per unit volume, we get from the stress strain graph. We get from the stress strain graph. So we get from, which is this area, this area, this area, this area. Area under stress strain graph is strain energy per unit volume. Area under stress strain graph, and area under stress strain graph is strain energy per unit volume. So it's half stress strain. Strain energy per unit volume is half stress strain. Area under stress strain graph. If FE graph, you get strain energy. If stress strain graph, stress, stress is the symbol stress, sigma, strain is epsilon. Under stress strain graph, get strain energy per unit volume, which is also half stress strain. So just calculate strain energy per unit volume. So stress is 10.5 exponent 7. So just calculate 10.5 exponent 7. Okay, and then for the strain is 1.5 negative 3. 1.5 negative 3. 1.5 negative 3. Then what do you get? Strain energy per unit volume. I get the answer 7.875 exponent 4 joule. Joule per meter cube. Why joule per meter cube? Because strain energy is joule. Volume is meter cube, isn't it? Joule per meter cube. That's the strain energy per unit volume. Joule per meter cube. That's the answer. Strain energy per unit volume. There is another way to find the strain energy if this force elongation graph is not drawn or is not provided. There's another way to find the strain energy straight away from the stress strain graph. How? From this formula, strain energy per unit volume is the half stress strain. It means you got this value. This value is strain energy per unit volume. So what you have to do is just find the volume. Just find the volume. Let us find the volume. Volume is area times length, isn't it? Area times length. So, the volume. The wire. You want to find. So the area. This is the area, and this is the length. So area times length is the volume. Area times length. What's the area I got just now? Pi d squared over 4 is 1.131 exponent negative 6. Just put in there. 1.131. This is 1.131. Negative 6. Negative 6 meter square is already in SI unit. Now, how about the length? Length is 3 meter. Length is 3 meter. Length is 3 meter. I get the volume. I got the volume. What's my volume? What's the volume I got? I got 3.393. 3.393. This is 9. Exponent negative 6 meter cube. That's my volume. So once I got my volume, I can find my strain energy. So my strain energy is actually from here, strain energy is 7.875 times 4 exponent 4. This one just multiply. Yeah. So here you multiply V. Yeah, just cross multiply the top. Yeah, because this whole thing is strain energy per unit volume. Maybe I just drop off this one. This whole thing is strain energy per unit volume. So what you have to do to find the strain energy is just multiply this V to the top. Then you can find my strain energy. Okay, so multiply the top, the volume. So what is the answer? I got just multiply by my volume 3.39. This one 3.393 exponent negative 6. Okay, I multiply that one, and my strain energy I get is 0.267 joule. The same as before, area under FE graph. I get back 0.267 joule for this one. Okay, So there's another way to find the strain energy. Another way to find the strain energy. If you don't draw the FE graph, you still can find the strain energy from stress strain graph. But it just you have to find the volume first. You have to find the volume to multiply to the top. Then you can find the strain energy. Okay, so very simple. Again, I want to tell you is this is a stress strain graph. Don't forget to check the exponent, the unit, and for stress strain graph, the gradient of stress strain is the Young modulus, and for the force elongation graph, the gradient is the force constant. And about the strain energy is area under force elongation graph. For the strain energy per unit volume is the area under stress strain graph. So strain energy is half Fe, strain energy per unit volume is half stress strain. I think that's it for this chapter. I cover almost everything. Yeah, hope you really liked the videos, and don't forget to like and subscribe. Anything you don't understand, please leave a comment below, and I will try my best to answer your questions as soon as possible. Thank you. Bye.